Okay, in the last lecture, we looked at the Bain strain, which converts a body-centered tetragonal cell of austenite into that of martensite by a compression along the z-axis and uniform expansion along the other two axes. And we demonstrated that if we represent the austenite as a sphere, then on the operation of the Bain strain, you can see two sets of lines which are unchanged in length, but they are rotated. So they are not the invariant lines that you need in order to have a glissile interface. Okay. However, if to the Bain strain we add a rigid body rotation, then we can produce one invariant line, but the other one goes out of coincidence by double the angle. Yeah? So with a rigid body rotation and a Bain strain, you can get an invariant line strain, so that satisfies the condition for martensitic transformation, and that extra rigid body rotation exactly predicts the observed orientation relationship. Okay. So the Bain orientation is of course not what we observe, but if we add the rigid body rotation that produces this coherent line, then that exactly predicts the orientation. But there is no way that we can get two non-parallel invariant lines. In other words, you cannot change austenite into martensite with a deformation which leaves a plane unchanged, okay, undistorted and unrotated. And yet, when we see the shape deformation looks like a shear on a plane. In other words, an invariant plane strain. So at this point, we have solved the orientation relationship, but the shape deformation is not consistent with the combination of the Bain strain and the rigid body rotation, and we haven't explained why we get the strange habit plane indices like 315, 10, and 259, and even those are approximate. Okay, so imagine that we've got a crystal of austenite, right? So this is all in your notes, so if you can just pay attention, right? So this is our crystal of austenite. When it transforms into martensite, we will observe a change in shape, which is approximately a shear, but there's also a volume change, right? So if I shear on this plane, I will get an object which looks like this. And that will be the shape deformation that we observe experimentally by looking at interference microscopy or any other technique which looks at topography. But it has to be the wrong crystal structure because you can't change austenite into martensite with a shear deformation. Okay, so just the shape deformation does not generate the body-centered cubic martensite. And that was found in 1940 by Greninger and Troiano, who applied the shape deformation to austenite, and it does not produce the right crystal structure. Okay? Right. In order to produce the right crystal structure, the total deformation must be an invariant line strain, equal to a Bain strain and a rigid body rotation. So initially we sheared on this plane. If we now shear on this plane, then where is the invariant line? Yeah, through X and out of the plane of the board, because this plane is left unchanged by this shear, and this plane is left unchanged by this shear. So that means this is the correct crystal structure, yeah, an invariant line strain, but it's not the shape that we observe. So this part of the deformation is invisible. We don't see it experimentally. Okay, so at least we've got the right crystal structure. Now, is there any kind of deformation which can make the shape equal to that, but which doesn't change the crystal structure? What kinds of deformation do not change the crystal structure, but change the shape? Yeah, twinning. What else? Slip. Yeah, so slip doesn't change the crystal structure, and similarly mechanical twinning doesn't do that. It simply reorients the lattice, right? So if I periodically slip this crystal so that the macroscopic shape becomes this, then the problem is solved. Yeah? So this is where we've twinned the crystal so that the macroscopic shape is this. We haven't changed the crystal structure by twinning. We've just reoriented it. And we predict that we will observe twins inside the martensite. So this was back in 1953, before transmission electron microscopes were used in materials. So this was predicted before it was observed, right? But it's not necessary just to be twin. You can also slip this crystal periodically, and what you would observe in a transmission electron microscope is a set of steps, slip steps. So macroscopically the shape is correct and the crystal structure is correct. This kind of deformation, which doesn't change the crystal structure, is called a lattice invariant deformation, right? That's the term that you find in the literature. So the problem is now completely solved, every aspect of the crystallography, because you see this average plane here can be anything depending on how much shear we have to add in order to correct the shape. Even if these facets here are crystallographically rational, like 1 on 1 and so on, the average plane depends on how much we correct the shape. And that's why the habit plane has strange indices, because macroscopically this is a strange plane, even though microscopically it's rational facets. Yeah? Okay? So if you follow this operation through mathematically, you can exactly predict the habit plane as well. When I say exact, of course, it's irrational, so we can't exactly predict it, but accurately predict it. And we predict that we will observe either twins or slip steps at the interface. So these diagrams here are a part of a plate. Here we have slip steps and here we have twins. When we have twins, we see twin interfaces inside the plate. Here we don't see anything inside the plate, but we see slip steps. Okay? And this is the first transmission electron micrograph showing periodic twinning inside the plate of martensite. The first observation of twins was on a replica, and that was by Shimizu in Japan, a carbon replica. But you can't prove that it's twins, but you saw these extremely fine features in the replica, and then when tin foil preparation became common, these were observed, which are transformation twins inside the martensite, very closely placed. You can see the scale here. This is of the order of 200 angstroms thickness. So it's one of the few theories where you make the prediction first and then you do the experimental observation. Generally speaking, we develop theory to explain what's already there, like the theory of the universe. The universe is already there. We are just expressing it mathematically, right? So this is a fantastic theory which really hasn't changed since 1953. It works very well. Now, we've looked at the transformation from face-centered cubic to body-centered cubic, and it can be tetragonal as well. It doesn't matter. But there's another kind of transformation we are interested in now, especially with things like high manganese steels and so forth, where you transform austenite into hexagonal close-packed martensite, right? In pure iron, you only find the hexagonal form deep inside the earth where there's a lot of pressure. Now, if pressure favors a phase, that means it must be a higher density, sorry. So hexagonal close-packed iron has a higher density than austenite. Okay? When you look at the structure of hexagonal close-packed iron, it's basically taking the, this is the austenite. So we have ABC, ABC stacking of the 1-on-1 planes. Yeah? If we alter that stacking sequence into AB, then we get the hexagonal close-backed ion. If you just look at this diagram, and we are treating this as a hard sphere model, then there should be no change in volume. All we have to do is every second plane we change from A to B, right? So this hard sphere model doesn't predict that there should be a volume change, but in fact the near neighbors are not the same, so you get a volume change as well. I will prove that to you shortly. So this is a simple shear. Yeah? If you pass a Shockley partial on one of the 1-1-1 planes of austenite, it changes the stacking sequence locally into a hexagonal close-backed array, a thin layer of hexagonal close-backed ion. But this model doesn't give you a volume change, whereas we know that the density of hexagonal close-backed ion is higher. But the point is, a simple shear changes the austenite into martensite, epsilon martensite. And the story stops here, that when we shear here, we not only have the correct shape, but also the correct crystal structure. So the habit plane of epsilon martensite is precisely 1-1-1. It's not irrational, because we don't have to do anything further. You simply shear the layers and you get the right structure and the right shape. Yeah? And the orientation relationship is very simple as well. What is the orientation relationship? Yeah? Yeah, the basal plane 0, 0, 0, 1 is parallel to 1-1-1, and the close-back direction inside the basal plane 1, 0 bar 1, 0, yeah? Or in 3-index notation it's 1, 0, 0, is parallel to 1, 1, 0 type in the austenite, precisely. So there's nothing irrational about hexagonal close-backed martensite, yeah? Because it's a shear deformation which changes the austenite into martensite. And we satisfy the condition for martensitic transformation because there's an infinite number of invariant lines inside that plane. Right, now these are transmission electron micrographs of stacking faults. And I explained to you that a stacking fault in FCC is a 3-layer thick hexagonal material, right? Because the local stacking sequence is AB. But where is the volume change? Now, why does the stacking fault appear like this in a transmission microscope with lines? Have you done any courses on TM? No? Okay, so inside a transmission microscope, say if this is my thin foil, right? Then I have a beam here, and the intensity of the beam oscillates like this as a function of depth, right? Because it's exchanging intensity with the diffracted beam. So if I put my stacking fault in here, then the intensity here is different from the intensity here. Yeah? So you get bright and dark fringes if the fault is inclined. So that is simply what we call depth fringes. Right? Similarly, if you have a dislocation which is inclined, you'll get bright, dark, bright, dark, bright, dark regions on the dislocation line. Those are not precipitates, those are just the fact that the dislocation is inclined. Okay? All right. Now, if I want to cancel out this contrast, then all I have to do is image the stacking fault with a G vector, that means a reciprocal lattice vector, which is at 90 degrees to the displacement vector of the stacking fault. So if the displacement vector is R, parallel to a Shockley partial Burgers vector, then G dot R is 0, the contrast should disappear. just like when you determine the Burgers vector of a dislocation, you do that by choosing a diffracting vector which is at 90 degrees to the Burgers vector, and then the dislocation disappears. Yeah? So, if you think about a dislocation as like this, then the Burgers vector is along here. Okay. So the displacements are parallel to the Burgers vector. So if I use a G vector which is pointing this way, then these planes are not distorted. Okay. These planes here are not distorted. So if I image using a vector, a G vector parallel to this, then the dislocation is invisible. And that's the way you determine the Burgers vector. You find invisibility conditions. Yeah? Find two G vectors where the dislocation disappears, and therefore you solve the problem for the Burgers vector. Right, so if I take G dot R in this case, the R is the displacement vector, as 0, then you can see the contrast disappears, right? But it hasn't disappeared completely. I can still see something. And that's because there's a volume change normal to the fault. Right? So this is the first experimental verification that a stacking fault is actually a hexagonal close-backed region. And if you change the lattice parameter by alloying, then the volume change will also be different, and this contrast changes. So these people took a series of 3 alloys in which the density difference changes, and demonstrated that the contrast, the residual contrast here, corresponds to what you would expect from different volume changes. Right? So it's brilliant. This is a nucleus of martensite, and it shows that it truly is hexagonal close back. It's not just a stacking fault. There's a volume change normal to the fault. Okay? So we've solved everything about the crystallography of martensite, but you are also interested in other aspects of martensite. For example, what temperature will it form at? The driving force for martensite, because there's no composition change, is very simple. If I have an alloy here and I form martensite, then this is the free energy change, right? There's no composition change. If I'm on this side and I transform to martensite, I get an increase in free energy. That's no good. That's not possible. So there is a point here to the right of which you cannot get diffusion-less transformation. Right? And if I plot the locus of that point as a function of temperature, I get a line which is called the T0 line, which doesn't appear in your phase diagram because it's not equilibrium, but you can easily calculate it using something like thermocalc or the free software on my website. So if I have austenite of this composition, it is possible in principle to get martensite. The driving force will be negative. Yeah? The free energy change will be negative. But if the composition is beyond T0, it's thermodynamically impossible to transform austenite without a composition change. Right? So this is purely thermodynamics, and we are talking only of the chemical composition of the austenite and ferrite. But we've already seen that we have a large shape deformation, therefore there must be strain energy. So you actually need to supercool below T0 in order to get martensite to allow for that strain energy term. Right, so this is the driving force that we are interested in. This is for the equilibrium transformation, and that will be larger than the driving force from martensite because we don't have a composition change and because there's a strain energy term here. Okay? So the difference between this and this is the strain energy. This is very large. Because the shape deformation is very large, this is huge, 600 joules per mole. Typically, when allotriomorphic ferrite or pearlite forms, it's of the order of 40 joules. So this is a very, very large strain energy, and that's why the transformation is dominated by strain. We get the thin plates forming. Yeah? If you have twins inside the martensite, then you have to add a further term, which is due to the interfaces, the twin interfaces. And the surface area of the plate doesn't really contribute much, because the surface to volume ratio is very small when you have a large plate. And then you might have some dislocations which add additional. So if you add all this up, it's about 700 joules per mole. And this is the free energy of austenite as a function of temperature and of ferrite as a function of temperature. And this is the driving force for martensitic transformation. If I plot this as a function of temperature here, at some point it reaches your 700 joules per mole, the critical driving force that you need to compensate for all the strain energy and so forth. That defines the martensite-start temperature. Okay? Now, this curve you can calculate very easily as a function of any chemicals that you wish to add to steel, because you have thermocalc and similar software, right? So you can easily calculate the driving force as a function of temperature. You work out when that driving force reaches 700 joules per mole, and that gives you the MS temperature. Everyone happy with that? So supposing I told you to make an alloy of iron and gold, you could calculate the MS temperature by working out the free energy for the iron gold system, setting it to 700 joules per mole, and you've got your martensite-start temperature. Okay. Now, of course, if I apply a stress, then the stress will do work. It will interact with the shape deformation. Just like when you pull a crystal, it slips, right? And the stress does work. So if I add that work to the driving force for transformation, then the effect is that the original martensite-start temperature is raised. Yeah? Because in addition to the chemical driving force, you've got the work done by the stress. So the stress can induce martensitic transformation above MS. Now, where do we use this? Trip steels. Yeah? So when you pull a trip steel, you're not cooling it. It's the stress which is doing the work of transforming the martensite. Yeah? So you can calculate the change in martensite-start temperature simply by calculating this work done by the stress. So how would I calculate U? So do you remember that we had an elastic curve here, and the area under the curve was the energy per unit volume? But of course this is not elastic, it's plastic. Yeah? So here we had half times the modulus times epsilon squared, and the half is because this is elastic. But if it is plastic, then there's no half term, it's just the area under that, right? So it's possible to work out U quite easily. What would we use as a strain? The shape deformation, right? Which is a shear of about 0.26 and a volume change. So simply multiply the shear stress on the habit plane by the shear strain and the normal stress on the habit plane by the volume change, and you've got the term U. So you can work out the change in MS due to the stress. And supposing that stress favors the formation of a certain orientation of martensite, just like in slip you have the Schmidt factor. Yeah? Not all slip systems are stressed equally. Then the change in the driving force due to just tensile stress is about 0.86 joules per mole per megapascal of stress, right? So if you're applying 100 megapascals of stress, then it would be 100 times this, okay, in joules per mole. If you are compressing, it still favors martensitic transformation, but to a lesser extent, because compression opposes the volume change, but the shear stress is still there. And at a crack tip, you have a combination of stresses. If I apply hydrostatic compression, that will oppose martensitic transformation because there's no shear stress with a hydrostatic compression. Yeah? So all this is fairly easy to work out. Okay, I won't go into this, but you can work out the effect of austenite grain size. This work was done by Hongsuk Yang, who was in GIFT. And this is the most cited paper that GIFT has ever published. Okay? And it shows how you would expect the martensite-start temperature to change when you reduce the austenite grain size. And the effect becomes important when you get to a grain size which is small. Right? Large grain sizes doesn't matter very much. Okay. And it's a very simple calculation actually. Always, if you have a simple calculation, people will use it, and therefore you will get a lot of citations. Yeah? But it works very well. Of course, you can see these are experimental data, and this is the calculated curve. So, Einstein's equation is just E equals mc squared. Right? Yeah? Okay, so I think we've done everything about martensite. And it's the only transformation where we can calculate everything. All the other transformations, involve diffusion, and not all of them. Bainite and Widmanstatten ferrite are different. But if you look at pearlite, allotromorphic ferrite, and so on, they involve diffusion. And diffusion is a very badly behaved phenomenon. Yeah? So, everyone assumes that you get equilibrium partitioning when these phases grows. Or you might get para-equilibrium, in which only the small atoms diffuse. But there's an infinite number of states between para-equilibrium and local equilibrium. There's no reason why it should follow equilibrium. So they are extremely difficult to model and predict. You have to make so many assumptions. With martensite, everything is solved. I'm exaggerating, but relative to other transformations, everything is solved. Okay, that's all there is for this course. So enjoy yourself now with the homework. Okay? Okay, thank you.